In the previous video, we looked at the laws of Boyle, Charles, and Avogadro, but let's see how we can combine them to come up with what we're going to call the ideal gas equation. Boyle says that the volume is proportional to 1 over the pressure, Charles that the volume is proportional to the temperature, and Avogadro that the volume is proportional to the number of moles. So if we take all of these three laws together, we can see that the volume is going to be proportional to N times T over P. And what we can do with this is we can say that rather than have this proportion, we can say that the volume is going to be equal to some type of constant R times N over T divided by P. And if we rearrange the variables in this particular equation, we get that pressure times volume is going to equal N, the number of moles, times R times T. And this expression right here is known as the ideal gas equation. So we need to determine what our constant is, and R is sometimes called the universal gas constant, which is 0.0821 liters times atmospheres divided by moles times Kelvin. And in this particular equation, we can say that an ideal gas is a hypothetical gas that behaves according to the ideal gas law under all conditions. And by using this ideal gas law, we're going to be able to predict with reasonably good accuracy some of the properties of our various gases. So we talked a little bit about temperature and pressure, and the temperature and pressure is going to influence the volume. So we need to come up with some type of standard as a reference point. And this reference point will be called standard temperature and pressure, which is abbreviated as STP. And you're going to see many problems that reference STP, and at STP our temperature is going to equal 0 degrees Celsius or 273.15 Kelvin. Our pressure is going to be 1 atmosphere, and the volume of a gas at STP is going to equal 22.4 liters. So, and that 22.4 liters is per mole of the gas. So every mole of gas is going to be 22.4 liters, our pressure is going to be 1 atmosphere, and the temperature is 273.15 Kelvin. So when we look at this ideal gas law, we can look at the various calculations here, and experimentally we can easily change the pressure, volume, and temperature, but the number of moles typically remains the same. So if we look at this PV equals nRT expression, and we rearrange this, we can say that the pressure times the volume divided by the temperature is going to equal N times R. Okay, R is a constant, but when we do a chemical experiment, typically our number of moles are going to remain constant as well. So if we start at a first set of conditions where we say P1, V1, and T1 is going to be equal to NR, we can then change the conditions of the pressure, the volume, and the temperature. And I'm going to say those are P2, V2 over T2. This is also going to be equal to NR. So if we set the NR equal to each other and set up this equation, we can derive something that says P1 V1 over T1 is going to equal P2 V2 over T2. Okay? And this typically allows us to start a reaction and use the initial conditions, and then we can look at the final conditions. And if we know the certain parameters we started with and we measure a couple of the ones that we ended up with, then we can solve for the other variable. So this can be determined, or this can be known as the combined gas law. And when the experimental conditions are changed for a fixed number of moles of gas, the combined gas law, which I'm going to put I'm going to highlight here, can be used to solve some of your problems. And it's derived right from the PV equals nRT expression from the ideal gas law. So these are the two equations that we can derive that are going to help you solve a lot of the problems that we're going to look at in this particular chapter. So in the next few videos, we're going to go over some various example problems using the ideal gas law, the combined gas law, and all of the laws that were proposed by Boyle, Charles, and Avogadro.